In this video, I want to introduce the idea of confidence intervals to you. Now, let me just say before I start that while we're going to be talking about confidence intervals for mu and working with the sampling distribution of X bar, the ideas expressed in this video are going to work for any confidence interval we run into. And later on in the semester, you're going to hear me talk about how they're just confidence intervals. Way too early, way too soon for me to be saying that. Unfair, completely unfair. But the idea is true. There's one confidence interval idea that can be applied a lot of different places. So let's start with someplace we've already been before. Now let me get a pen that'll help me with this journey. So we're going to start with a definition we saw with sampling distributions, and that's the idea of a point estimate. A point estimate is a sample statistic that provides the best guess at the value of a population parameter. The idea is there's a population out there and there's a parameter, call it mu maybe, that I don't know about. I want to learn about this value mu, but I don't know what the value is. So we take a sample. We take our sample and we calculate the statistic that we think does the best job at estimating mu. In this case, it would be the sample mean, X bar. So what we want to do here is estimate mu. In today's discussion, I'm going to talk about working with a large sample. For our purposes, we've talked about how a large sample, when you're working with a population mean and working with the sampling distribution of X bar, is a sample of size 30 or more. Now, the caveat, the big caution is there are lots of sample size criteria. Depends what you're doing, what you're analyzing, how you're doing it, but you always want to be mindful of how big a sample do I need to be considered a large sample. For us, in this case, N has got to be greater than or equal to 30. That's what we're going to consider a large sample when working with means. We will be able to work with a small sample estimation of a population mu, but this discussion today in this video is just large sample. So here's what we know. The point estimate, our best guess, is X bar, the sample mean. We learned three things about the sampling distribution of X bar. When I had the conversation with you about sampling distributions, we learned that the mean of the X bars is centered at mu. We learned that the standard deviation, sometimes called the standard error, but the standard deviation of the sampling distribution of X bar isn't sigma. It's sigma divided by the square root of n. And when we have large samples, the central limit theorem will let me know that the shape of the distribution is going to be approximately normal. In your notes this semester, and I'll start you off now, you're going to see CLT, central limit theorem, CLT in parentheses, and that's when we can apply that theorem to get normality. So that means when we draw pictures of this, and please have a little grace, I'm drawing with a mouse. That ain't bad. If I pile up the X bars, remember that sampling distribution idea, take a sample, calculate a statistic, do it over and over and over again, and pile them up, they're going to be centered at the population mean mu. That's what we know. So we're going to start with that. So I've drawn a sampling distribution of X bar here. And what I want to do is go and put in these values 1.96 standard deviations below X bar, 1.96 standard deviations above X bar. Kind of weird numbers, right? Usually I think plus or minus 2. I'm going plus or minus 1.96. And what I want to ask is, what's the probability X bar falls in between these two values? So I'm trying to shade the region in here. I'll go shade it this way too. What's this probability right here? Well, we know how to do this. And it's going to be a little ugly, but how do you solve normals? Well, one way of doing it is to change them to standard normals. But I'm going to use the z-score transformation when working with X bar. Sometimes I refer to it as the X bar version of the z-score. And you can see I'm going to take this value and subtract the mean of the X bars, which I'm doing here, divide by the standard deviation of the X bars. I'm going to take this value and I'm going to create a z-score for it. Subtract the mean of the X bars, divide by the standard deviation of X bars. But what we've said is the mean of the X bars is equal to mu. So those two things just cancel. Same thing over here. The standard deviations of X bar cancel, and what we're left with after all is said and done, after all the ugliness in Greek letters go away, is we're left with this. What's the probability that my standard normal random variable z is between a negative and a positive 1.96? And we've done this. We've looked up, these are X bar values, say here. If I go to my z table, or if I use my Excel functions, I can find the probability less than a z-score of 1.96. I can find a probability a z-score is less than a negative 1.96, and we saw the way to solve that is to get those numbers and subtract them. So when you look up a 1.96 in a z-table, you're going to see a 9750 number. When you look up a negative 1.96, you're going to see an 0.25. So the probability all the way over is 9750. The probability in this little region that I'm shading now is 0.250. So that means the probability in between these two is the difference between them, 95%. In repeated sampling, 95% of the X bar values will fall between those two arbitrary starting points that I picked. Now that 95% numbers we're going to find out is tied to the plus and minus 1.96 number. That's going to be the confidence level, and I'll give you that term on another slide here in a bit, but that's going to be the confidence level we use when we're working with the values 1.96. And probably a better way of saying it, 1.96 is going to be the number we use from the z-table when we're using a 95% confidence level. Now that only works for large samples. All right, if we're working with small samples, something else is going to come into play, which we'll talk about later. But that's the idea. 95% of the X bar values will fall between there. All right, now that's step one. Hopefully that makes sense. I'm just doing stuff we've done before, working with the sampling distribution of X bar. Here's step two, and this is what I would call, I'm going to give you a big asterisk over here. This is what I'm going to call your confidence interval picture. This is the one that hopefully will explain how confidence intervals work. You can see I'm starting with the same picture we just had, the normal distribution. It's centered at mu here. Let me write mu in here. I have 1.96 standard deviations above, 1.96 standard deviations below. And the idea is we're going to repeatedly sample and construct the intervals X bar plus or minus 1.96 sigma sum X bar. Let's start with the X bar. Let's start with that. So here's what we know. Here's what we said. If I take a sample and calculate a value of X bar and do it again and again and again and again and again, they pile up into this distribution that we call the sampling distribution. So here's what I want you to think. If I was to sample all the time, over and over and over again, I would see the whole distribution. But we don't get that. We don't have the luxury of seeing what would happen if we did it over and over and over and over again, because we just want to do it once. So what this picture is designed to do is to think you through that process. Now, what I mean by that is, let's say we're working with Mustangs. Let's say I want to learn about all the Mustangs in a given county. Okay, I want to learn, and we go onto one of our car websites and we find that there are 604 Mustangs for sale currently in whatever county you happen to be looking at. I don't want to sample all 604 of them. I sample 25 of them. Oh, nope. Today I sample 30 of them, right? Because I want a large sample. I sample 30 of them, and I find the average price of my 30 Mustangs. Now, I know if I did this over and over and over again, I'd get this normal curve, this normal distributions, but I'm only doing it once. So my average of 30 comes somewhere from this distribution. So let me draw. Let's see if I can draw a nice little point. Maybe my value of X bar falls right there. Now, the tricky thing, one of the tricky things is I don't know where mu is, so I don't really know where to draw my value of X bar. If my sample price was, or sample mean price was 15,000, I don't know if the mean of all is greater than that or less than that. So let's just draw it in here somewhere. That's my point estimate. It's a single value. But this says don't just look at X bar, add and subtract 1.96 standard deviations of X bar. So a great question is, okay, what's that? Well, let's say I'm standing right here at mu and I decide to travel over here. I traveled 1.96 standard deviations of X bar. Likewise, if I went over to this one, if I went from mu there, I subtracted that. So what we're saying is take a look at the distance between these two things and add it to our value of X bar. I'm going to put a parenthesis here. And then subtract it from our value of X bar. And what you get is a lower endpoint and an upper endpoint up here. You don't get a point estimate, you get an interval estimate. Now notice, in between this lowest value here and this highest value here is the value of mu. The endpoints of this confidence interval captured mu. And that's true if you start with an X bar value right here. All right, so maybe those are my 30 Mustangs, but let's go to your 30 Mustangs. Let's say you sampled 30 different Mustangs. You got a different value of X bar. Maybe your value of X bar is right here. Man, look how close it is to mu. Do you know that? No, of course not, because you don't know the value of mu. But let's just say, for the sake of argument, that's where your value of X bar fell. Great sample, by the way. Well, again, we're not going to look just at the X bar value. We're going to add and subtract 1.96 standard deviations of X bar, and we're going to get an interval estimate, but like mine, yours also captures mu. Let's keep going. Let's go to somebody else. Let's say they get a value of X bar. Look how lousy, look how far this value of X bar that I'm drawing in here falls from mu. And yet, when I do my 1.96 standard deviations of X bar thing, I probably went too far there, it just barely would capture it. it also is a good interval. And then we go on and on and on and on, and we do this forever. We calculate a value of X bar. We do our 1.96 standard deviations X bar. We create intervals, and they move around. They slide. And what I've called them over the years, and when you repeatedly sample, these things are referred to as my dancing intervals. They dance around the value of mu. The 4 I've drawn on the screen right now, they're all what I'll call good intervals because they've all captured mu. Every single one of them has mu in the middle of it. All right, maybe not smack dab in the middle, but in between the endpoints. That's the key. Are they all going to be good? Hopefully you know the answer to this. The answer is no, they're not. Let me change my pen color now. Let's go to, I think I can change the ink color. Yeah, I can. Let's go to a nice blue. Let's say your value of X bar falls out here. Now I'm in the lower tail, but I have the same kind of idea, same kind of argument when I'm in the upper tail. When the value of X bar falls outside those lines, watch what happens when I do my 1.96 thing. It's going to come up a little bit short here. When I go 1.96, it goes real far that way. This is a bad interval. The blue interval I've drawn here, I think it's blue, maybe it's black, that's a bad interval. It missed, right? The value of mu falls outside. Likewise, if I put a value of X bar down in the upper tail or up in the upper tail, then you'd also get a bad interval over there. And so that's the idea. If you were to sample over and over and over again, some of the intervals would capture mu, some of them won't. In fact, because of what we said on the prior screen, what you should see here is every time the value of X bar falls between these lines, you're going to get a good interval. Because that's the distance that you're adding and subtracting from the value of X bar. So every time X bar falls in between those points, you get a good interval. And here's our interpretation. This is sometimes going to be referred to, or later going to be referred to, as a theoretical interpretation. You'll see that in a bit. If I was to repeatedly sample, and typically we say it in repeated sampling, 95% of the intervals created would contain the population mean mu. In repeated sampling, 95% of the intervals created would contain mu. We call the one interval we actually construct a 95% confidence interval for mu. And now let's get some terminology out of the way. 95% is referred to as a confidence level. If you express it as a decimal, it's called the confidence coefficient. If you turn it around and think about the other part of it, if it's 95% confident, 5% is your anti-confidence, your unconfidence, your error rate. And we actually give the error rate a symbol. We're going to use the symbol alpha. The Greek letter alpha is going to be the symbol we use for the error rate. And so that's the starting point. That's the theory of confidence intervals. We take a sample, we calculate a statistic. Now we bound it. We go around it 1.96. And that number 1.96, again, is tied to the 95%. If I use a different number here, well, that's going to change the percentage it's in between. And typically we start there. We start with our percentage. What if we want a 90%? What if we want a 92%? Well, that's going to change the 1.96 number. So that's how I want you thinking about confidence intervals. It's the repeated nature. So let's have one more slide on this video, and then I'll stop and we'll come back. Estimating mu with a large sample. Here's our formula. It's going to be the X bar plus or minus something like a 1.96, which you're going to get from a Z table. And I'll show you how we use that in a little bit. Times the standard deviation, sigma over the square root of n. And typically we don't know sigma, so we plug in a value to sample standard deviation in our calculations, and we'll see how the software is going to do that. Most calculations will be done by the software. Depends on the software how much calculations are going to be done. What Excel will do is it'll tell you what the sample mean is, and it'll tell you what this part here is, sometimes referred to as the margin of error. It'll give you that part for the level of confidence that you want. So when you ask statistics to do a confidence, when you ask Excel to do a confidence interval, it's going to ask what confidence level do you want? You're going to say, oh, I want 95%. It's going to give you the 1.96 times S over the square root of n. It gives you this whole piece. And so you got a little math to do. You're going to have to take the X bar value and add that piece. You're going to have to take X bar value and subtract that piece. But that'll give you the confidence interval endpoints. So finding the endpoints to the confidence interval is relatively straightforward with the software that we're going to use. You're going to be responsible for knowing the Z value to use, knowing that 1.96 works with a 95%. I'm going to show you, we'll start on the next video. I'll show you how to find those Z values using our Z table this semester. But interpreting the interval, how do we do that? Knowing sample size requirements, knowing assumptions, that's a topic that I'll get into. Right now, the only assumption we need is a nice random sample. but we'll talk more about that in future work. So that's a good place. I'm 15 minutes in. That's a good place to stop this video. I'll come back and we'll talk about finding z-values and interpreting confidence intervals. See you in part 2.